So for starters, what makes something a differential equation? I have to have a derivative, that's the differential part, and an equal sign. That's it. I gotta have a derivative and an equal sign. It's a differential equation. So some kind of differential equations that we've sort of been doing, even without saying that we were doing. If I wrote something like dy dx is equal to x squared plus 3 sine x, and then I asked you to solve for y, technically you were solving a differential equation. Now really, we did that in the context of thinking about finding an antiderivative, or saying this is somebody's derivative, who was that somebody? Well, the more formal way to think about solving this differential equation and kind of tying that back to the idea of antiderivatives and integration, if I look at this, the only variable that I have over here is x's, and over here I have a dy dx. And what I can do is multiply both sides of this equation by dx. When I do that and rewrite it, so over here, my dx's cancel out, and I have dy is equal to, and then over here, I've got x squared plus 3 sine x dx. Both sides now have a differential or a d something term. And if I integrate both sides, then on the left-hand side, there's an invisible function hiding here, and that's the invisible function of the number 1. So on the left-hand side, when I compute this integral, I get y, technically plus a constant. So I'm going to put a plus c here. On the right-hand side, we're just doing the same antiderivative stuff we've been doing all quarter. So I'm thinking about who's the function whose derivative is x squared. I'm going to add 1 to the exponent, divide by the new exponent. Who's the function whose derivative is 3 sine x? Well, that's negative 3 cosine x. And then technically, on this side, we would need a plus c also. But these are two separate integrals we worked. So this constant isn't necessarily equal to this constant. And whatever this constant is, if I call those constant 1 and constant 2, I could rearrange this to say y is equal to 1/3 x cubed minus 3 cosine x plus c2 minus c1. But this whole thing, if c1 and c2 are just constants, then I can get rid of that whole thing and just call it a big C. So technically, that's what we've been doing for most of the quarter. We see this thing, we find an antiderivative, but in the background, we were secretly solving a differential equation. Okay. If I asked you to solve this, oops. If I asked you to solve this, it looks a little bit different from the ones where we were just finding the antiderivative, but it's not. The only thing we've done is change up the letters. There's this additional piece out here, and this we refer to as the initial condition. It doesn't actually have to be with a time equal to 0 to be an initial condition. We just refer generally to this additional piece of information as that initial condition. So I'm going to start off the same way that we did the other one, which is I'm going to multiply both sides by dt just to make sure that I have all my t's on the right-hand side and my dn alone on the left-hand side. So if I rewrite this to say dn is equal to, and I'm going to go ahead and multiply my dt over there, but I'm going to change that square root of t to say t raised to the 1/2 power. And then I'm all ready to integrate both sides. I'll integrate the left-hand side for you, and I'll give you a minute to integrate the right-hand side on your paper. Because we have an initial condition, we're not quite done yet. We want to take into account that initial condition. And this says, notation-wise, that when t equals 0, n equals 4. And we're going to want to plug those in so that we can solve for that constant. So n needs to be 4 when t is 0. 0 to the 3 halves divided by 3 halves plus 4 times tan inverse of 0 and then plus a constant. Just as a quick reminder, this is saying what's the angle where tangent of that angle is equal to 0. So tan inverse of 0 is 0. So this piece went to 0 and this piece went to 0, which means our constant is equal to 4. And our final answer for this problem would be to say that n of t is equal to this thing we found. And I'm going to go ahead and take that division by 3 halves and flop that around to be multiplication by 2/3. So I have 2/3 t to the 3 halves plus 4 tan inverse of x plus, and we found that our constant was equal to 4. And that would be my final answer for the solution for this. An autonomous differential equation, because on the right-hand side here, the only variable we have is the variable from the numerator in our derivative. So we are a pure time differential if everything is in relation to the variable in our denominator, and it's autonomous if everything is in relation to the variable in the numerator. Then I'm going to employ that same kind of technique that I did a minute ago, where I multiplied both sides of the equation by dx. Well, if I come in here and I multiply both sides of the equation by dx, then the problem on the right-hand side is that if I were to try to integrate this, I'd be integrating something of y with respect to x. So I actually need to do an extra step, and this is usually called separation of variables. I need to make sure that all of my y's are on that left-hand side with my dy term, leaving just the dx alone. So we're kind of going to rearrange this a little bit. So I'm going to leave this 3 over here with the dx because that 3 doesn't have any y's in it, but I am going to divide by y and y minus 1. Now it's not super pretty to look at, but if I rearrange this, we now have something that looks like this. And we can integrate both sides. That right-hand side, if I integrate 3 dx, that one's not too bad. I'm going to get 3x plus a constant. And on the left-hand side, well, now I need to remember all of those techniques of integration. So all those techniques of integration that we had from chapter 6, we might end up needing them in chapter 7. So I look at this and I say, well, it's just algebra. There's no u substitution because I don't have something on top to save us here, but the bottom does factor, so I'm going to need partial fractions. And extra bonus, you know, we're just, what, 3-4-ish weeks away from finals? Might as well start practicing all those techniques of integration. So I'm looking at 1 over y times y minus 1. And if we're going to do partial fractions on that, the green is not showing up super bright on my screen. I don't know if it's showing up better for you. Let me try red. I'm going to break that up as a over y plus b over y minus 1. If I multiply both sides by that common denominator of y times y minus 1, And over here, stuff cancels out and I'm left with a 1. And over here, when we distribute it in, A will end up with a y minus 1 term attached to it, and B will end up with a y. We had 2 different methods for solving it from this point. We can either plug in values for y or multiply everything out. I'm going to give you all 1 minute to solve for A and B. Your choice of whether you want to plug in numbers or multiply everything out on the right-hand side and match up coefficients. Bringing that back around here, that means we end up with, let's see, the minus sign was on top of the y, so I'll have negative 1 over y plus 1 over y minus 1. So on the left-hand side here, oops, missing my dy. So I still need to integrate this. And if I integrate negative 1 over y, I'll end up with negative natural log of y. When I integrate this, I'll end up with natural log of y minus 1. Oops, is equal to 3x plus a constant. Now this time I did not give us an initial condition, so we don't have anything to worry about solving for C. I'm going to preemptively ask a question for you. A lot of times when we're doing these problems, it kind of depends whether we're having to write answers on paper or we're putting answers into a computer system. But one of the questions that I get asked is, do we have to solve that to make it say y equals? Usually if you're turning stuff in on paper, no, you do not have to rearrange that to say y equals. But just in case anyone is working on some WebAssign problems and you have to rearrange something that looks like this, let's just take a minute to walk through the algebra on that. On the left-hand side, because I've got a couple of natural logs, I'm going to start by using log rules. That minus in front of the ln of y means that I could think about this flipped the other way. Ln of y minus 1 minus ln of y. And when we have subtraction between logs, that turns into division. So I'd have y minus 1 over y is equal to 3x plus a constant. And if we keep that going, how do I undo a natural log? Well, I raise both sides as e to the stuff. So on the left-hand side, that natural log will go away and I'll have y minus 1 over y. And on the right-hand side, we'll have e to the 3x plus a constant. There's another trick that we do here that's one part algebra trick, one part calculus trick. So here's the algebra part. If I had 5 to the 2 plus 7, that is 5 to the 9th. But this could have come from something that looked like 5 squared times 5 to the 7th. That's our additive law of exponents. So that addition in the exponent between the 3x and the c means that I can rewrite this as multiplication between two things that both have a base of e. So I've got y minus 1 over y, and then over here I'm going to rewrite that to say e to the 3x times e to the c. There's a very common calculus trick that we do at this point, and it's kind of similar to the thing I did moving the constants together in that other problem. Whatever the value of this constant is, and I'm going to give it a little subscript of 1, whatever the value of that constant is, because it's just a number, e raised to that number is also a number. So one trick that we do is to just rewrite that e c to the 1 and call that a new constant c. So this would look like y minus 1 over y is equal to c e to the 3x. We are almost there in terms of solving for that y. I hate fractions. both sides of this equation, or this side of the equation has a fraction on it. So I'm going to multiply both sides by y. On the left-hand side, those y's will cancel out, leaving me with y minus 1 is equal to c e to the 3x times y. Now you might be thinking, well, wait, can I just suck up the y with that constant too? No, because this one's a constant and this one's a variable. Can't mess with that y. Okay, I'm trying to get the y by itself though, which means I got to get all my y's on one side of the equation or the other. I'm going to choose to add the 1 over and subtract this stuff over to the left. So I'd have y minus yc e to the 3x is equal to 1. Now I can factor out that y and have 1 minus c e to the 3x is equal to 1. And I got no space anywhere, but y would equal 1 divided by all of that. Sure. I'll put it right there in the middle. So I'm going to have y is equal to 1 over 1 minus ce to the 3x. And in case you were wondering or wanting to play around with it, you might remember that this is more or less the general form for our logistic growth equation. So if you were to put this graph into Desmos, it should do one of those logistic growth kind of curves. So this equation is neither pure time nor autonomous, because if I look at the bottom variable of x, this has more than just an x in it. And if I look at the top variable, this has more than just a k in it. So it's not pure time and it's not autonomous, but it is separable. I'm going to start the same way that I started the other two, which is to multiply both sides by dx. And it's really that dx in the denominator that dictates which side of the equation I have to move which variable to. So I have to separate the x's and y's so that we can integrate them. Because that dx is on the right-hand side, I need my x squared to stay over here. So I'm going to divide by that k to the 3/2. So on the left-hand side, I'll have 1 over k to the 3/2 dk is equal to x squared dx. Once I have my variables separated, then I can integrate. Oh, and I'm going to go ahead and give us an initial condition here. So let's say that k equals 8 when x equals 1, and we're going to solve for k as a function of x. Okay, now I'm almost ready to integrate. Right-hand side is ready. On the left-hand side, I'd really like that to say k raised to a power so that I can add 1 to the exponent, divide by the new exponent. Because that k to the 3/2 is in the denominator, I'll go ahead and rewrite that to say k to the negative 3/2 dk. And over here, I've got that x squared dx. Now I'm ready to integrate both sides. On the left-hand side, when I add 1 to the exponent, I'll be at k to the negative 1/2 divided by negative 1/2. Can I take that back? I'm going to call k 4, because I would much rather take the square root of 4 than the square root of 8. Okay. So that's my left-hand side, and over here on the right-hand side, I'll have x cubed over 3. It doesn't actually matter which side we put the plus c on, but we should really only add it to one side or the other. It doesn't magically cancel out We're just combining the two constants together. We can rearrange this to get that k by itself now. Well, for starters, I'm dividing by -1/2 is the same as multiplying by -2. So I'm just going to do that instead and multiply by -2. Then my k to the -1/2, I can choose to rewrite to say that's the same thing as the square root of k, but in the denominator. So this side would look like -2 over the square root of k, and over here, I've got x cubed over 3 plus a constant. Now, because I asked us to solve for k, we have a choice to make. We can either look for that constant right now, or rearrange it to make it say k equals first, and then find the constant. Usually it doesn't matter which choice we make, so I'm going to go ahead and keep doing the algebra to get the k by itself. Let me just give myself a little more space. So -2 over the square root of k is equal to x cubed over 3 plus a constant. I changed my mind. I'm going to solve for the constant first. So I know that k needs to be 4 when x is equal to 1. So that tells me that -2 divided by the square root of 4 needs to be equal to 1 cubed over 3 plus a constant. Square root of 4 is 2. -2 over 2 leaves me with -1. So I've got -1 is equal to 1/3 plus a constant. And if I subtract the 1/3 from both sides, that constant is going to be -4/3. Now that I know what my constant is, I can change this equation to say -2 over the square root of k is equal to x cubed minus 4 all over 3. And notice I've plugged in the -4/3, and because they have a common denominator, I combined the top together. I just figured that'd be easier because now I can multiply both sides by the square root of k and multiply both sides by 3 and end up with -6 is equal to x cubed minus 4 times the square root of k. Divide by this, square both sides. So I think my k of x is going to look like that -6 over x cubed minus 4, whole thing squared. So it is a differential equation because I have a derivative and an equal sign. It is not pure time and it is not autonomous because I got x's and y's mixed up all over the place. But it is separable because there's a way to move all of the x's to one side and all of the y's to the other side. The first thing that I can do is to divide both sides by x squared. That's kind of our low-hanging fruit, as people like to say. So if I divide both sides by x squared, then at least this becomes dy dx is equal to x times e to the x plus y. Now, it may not be immediately obvious how to separate this last part, but I'm going to use that same trick that we used a few minutes ago, where I have addition in that exponent, and I'm going to break that apart to say e to the x times e to the y. So this will become dy dx is equal to x e to the x times e to the y. Now I'm ready to separate those variables. When I go to separate, starting out the same way, I'm going to multiply both sides by dx. By the way, that's also consistent with, I just don't like to have denominators on my fractions. So I multiply both sides by dx, and then I look at this side and say, these two pieces have x's, but that e to the y doesn't belong there. So I'm going to take that e to the y and divide both sides by e to the y. On the left-hand side, dividing by e to the y, since that's in the denominator right now, I can rewrite that to say e to the negative y dy. And on the right-hand side, I'm left with x e to the x dx. I think we have time. I am going to give everybody a couple of minutes to try to integrate both sides of this equation. Get rolling together. So I integrated the left-hand side for us. When I integrate e to the negative y, I get e to the negative y, but I have to divide by -1 because I have that constant multiplied by the y. On the right-hand side, we're going to have to do integration by parts. So I'm going to come off over here just so I have enough space. So if I integrate x e to the x dx, I look at that and it's a mixture of algebra and exponentials. So I'm going to think back to our acronym LATE. Since I've got a mixture of algebra and exponentials, we'll let u be equal to x, and dv will be that e to the x dx. When I take the derivative of x, I get 1 dx, and the antiderivative of e to the x is e to the x. Now I'm working on that ultraviolet voodoo. So I've got uv x e to the x minus the integral of v du. Well, that's e to the x dx. When I integrate e to the x dx, I just get e to the x back. And then we'll remember to add a plus c. This particular time, I didn't ask us to solve to make it say y equals or even to make it say x equals. So I would walk away and call that my solution.